Hi everybody. In this video we're going to be looking at eigenvalue problems as they pertain to differential equations. So let's go down, let's not waste any time, let's take a look. So what we're going to be doing is we're going to be thinking of the derivative as a function of functions. So I'm going to denote the derivative function, sometimes they call it, very often they call it the derivative operator, that is going to take a function, and what does it do to the function? It's going to produce a new function, which we denote by f prime. So it just differentiates that function. So it's a function of functions. You plug in a function, you get a new function out. You also have the second derivative operator. If I plug in a function, it spits out the second derivative of that function. Now, these operators, the derivative operators, and I could go to the third or fourth or fifth derivative, these are linear. What does it mean to be linear? Well, linear means that, if you have a transformation that's linear, that means that if I take the sum of two things and apply this to that, I get the sum of the outputs. So the function of the sum is the sum of the function values. And moreover, if I take a real number times the argument that I plug in, that real number can be pulled out. This is what it means to be linear. And it's not too difficult at all to verify that the derivative operators are all linear. They all satisfy these properties. These are just properties of the derivative. Now, when we deal with functions, we can think of functions as vectors living in a vector space. Now, this may seem strange to you because usually when we talk about vectors, we think about these, lines with arrows, something with a direction and a magnitude. Well, I'm not going to go through all the details of this, but I'm just going to point out that a function can be thought of as an infinite dimensional vector, where every single value of the function is a component of that vector. So it's like every value of x corresponds to a different component. And so we have this infinite dimensional vector. And with vectors, we know how to add them. We know how to multiply them by real numbers. Well, we can do the same thing with functions. We can add them. We can multiply them by real numbers. It all makes perfect sense. All those things we know about a vector space work for functions. We have to be a little bit careful about how we define the space of functions that we're working with, how many derivatives they have, and what their domains are, if they're continuous or not. And I'm not going to go into all the details of that, but if we deal with reasonably nice functions, they will be a vector space of functions. And so when I have a linear mapping on a vector space, a linear function on a vector space is called a linear transformation. So these are actually linear transformations. Now, when you have a linear transformation, you know from linear algebra that one thing you can look for are eigenvalues and eigenvectors. So we're going to be dealing with this guy right here. So what does it mean to be an eigenvector? Well, it means that when I apply it to a function, it's going to produce a multiple of that function. So lambda here is a scalar. It's just a real number. Now I'm actually going to put a negative here. And this equation is the equation for eigenvectors. This guy here is the eigenvector. Now we're going to call it the eigenfunction, just to be clear that it's a function, but you could call it an eigenvector if you wanted to. This is the eigenvalue. The real number is the eigenvalue, the function is the eigenfunction. So this is not going to happen to every function. It's not always the case that when you take the derivative of something, you get a multiple of it back. In fact, that almost never happens. But for some functions, it does happen. And for those functions, we call them eigenfunctions. And that multiple we call that, well, the negative of it, we call it the eigenvalue. Okay, well, let's look at this equation in just a different light here. I'm going to replace d squared with what it does. It takes two derivatives. So what we're looking at is we're looking at the differential equation y double prime equals minus lambda y. Let's add this to both sides. So we are really just investigating this differential equation. The solutions to this differential equation are the eigenfunctions, and the values of lambda are the eigenvalues. Now I have to point out one important thing here. We never let a trivial function count as an eigenfunction. So a function that's identically zero, that's zero everywhere, doesn't count as an eigenfunction. So we're looking for non-trivial solutions to this. So we are looking for constants lambda, the eigenvalues, and non-trivial solutions, the eigenfunctions y. Now, when we do this, we are going to specify what are called boundary conditions. What are those? Well, what we've looked at in the past have been called initial conditions, where we specify the values of the function and its derivative at a single value. Well, another thing that you can do is you can specify, instead of looking at the value of the function as derivative at a single number, you can look at the value of the function at two different numbers. And these represent boundaries of some interval. And that's one type of boundary condition that we're going to be exploring. So the boundary condition that I just described is this. Now, what is L? Well, we are imagining that the function is defined on the interval from 0 to L. Okay, so what I'm saying here is that here we have the interval 0 to L, and we're looking for solutions to this differential equation such that the solution's equal to 0 here, and it's equal to 0 here. It's pinned down at the endpoints of the interval. In between, we don't know what it does, right? But we're just requiring that it's pinned down at these endpoints. We are going to consider different boundary conditions later on, but I want to focus on these for now, okay? So we now have a theorem that we'd like to talk about with regards to these eigenvalues and eigenfunctions. The theorem says that the differential equation that we're considering, the eigenvalue problem, with these boundary conditions, the ones that we described up here, has a non-trivial solution, so that'll be an eigenfunction, if and only if lambda is positive. Okay, let's prove this theorem. So to prove this theorem, we're going to start by supposing that this differential equation has a non-trivial solution. Non-trivial solution. Okay, we're going to let y be a non-trivial solution. And the trick here is going to be to multiply both sides of this equation by y. That's not at all obvious, but that's a good trick to learn if you want to study differential equations. Okay, this trick can be used again and again, and it is surprisingly useful. I'm going to multiply through by y. Now I'm going to solve this for lambda y squared. Okay, and now what we're going to do is we are going to integrate this from 0 to L. And let's see what happens. What can I do on the right-hand side? I can integrate by parts. So I integrate this by parts, and then I need to evaluate it, everything from 0 to L. Well, let's evaluate this thing from 0 to L. Now, what are our boundary conditions? Our boundary conditions say that y of 0 is equal to 0, so that piece is gone, and y of L is equal to 0, so that piece is gone. So really, we've reduced this to the following. Okay? Now let's think about this. The right-hand side is the integral of something squared. So that means that this in here is always non-negative, so the integral is non-negative. The right-hand side is non-negative. Now let's look at this. This is something squared, so that's non-negative. And lambda is a constant. So lambda cannot be negative. If lambda was negative, this would be negative, the right-hand side would be non-negative, and we'd have a contradiction. So we can see that lambda must be non-negative. Now we need to show something a little bit stronger than that. We need to show that lambda is positive. So why can't lambda be 0? Well, let's think what would happen if lambda were 0. If lambda were 0, then this whole left side is 0. But that means that the right side is 0. Now look at this quantity. This thing is always non-negative. So the only way this whole thing can be 0 is if this is constantly 0. That means that y prime is always 0. If y prime is always 0, that means that y is a constant. But look, y is equal to 0 at 0. So if it's a constant, it must be equal to 0 everywhere. But that's a contradiction, because we said let y be a non-trivial solution. That's part of our hypothesis here. It can't be 0. So if y is a non-trivial solution, that can't happen. So that means lambda can't be 0. The only possibility left over is that lambda must be positive. So therefore, lambda is greater than 0. And so what we've done here is we've proven this direction of the theorem. We've proven that if we have a non-trivial solution, then lambda is positive. What about the other direction of the theorem? What if lambda is positive? Can we show that this differential equation has a non-trivial solution, a non-zero solution? Let's see if we can do that. So suppose lambda is positive. Okay, then we're looking at the differential equation like this. Now remember, back when we talked about how to solve second-order differential equations with constant coefficients, we learned how to solve this. So review that if you don't recall. What we get is now I'm using the fact that lambda is positive here. Now we also have these boundary conditions. Okay, well let's look at these boundary conditions one at a time. Y of 0 equals 0. What does that tell us? Well, if we plug in 0 for x, this whole term is 0 because sine of 0 is 0. And this term is equal to 1, so C1 must be 0. So this term's gone. What about the other boundary condition, y of L equals 0? Well, that means that this is equal to 0. There are two possibilities. C2 could be 0, or L could make this 0. Well, if C2 were 0, we would be getting the trivial solution. We want to show that you can get a non-trivial solution. So let's not consider that case. How can this be 0 without C2 being 0? Well, if what's in here is a multiple of pi, right? So that being 0 must mean that this is some n times pi for some integer n. Oops. Let me move out of the way. Okay, well, we can solve this for lambda here. That means that lambda is equal to n squared pi squared over L squared. And we see what our solution is. Our solution is some multiple, I wrote C2 before, I'll just replace it with C, times the sine of oops, it's the square root of that, isn't it? Okay. Try that again. N pi over L x. Okay, this is our solution. Now notice there are lots of different possibilities. We get a different possibility for every integer n. When n is 0, it doesn't count because it's the trivial solution, but we get a solution for every non-zero integer n. Okay. So we've proven both directions of the theorem. Okay. We've proven that if we have a non-trivial solution, then the eigenvalue must be positive, and if the eigenvalue is positive, we have a non-trivial solution. In fact, we have infinitely many, one for every integer n. And from all this, we can deduce a corollary. The corollary is that the eigenvalue problem that we were just dealing with has an infinite sequence of eigenfunctions. They all look like this. I might call each one yn, with corresponding eigenvalues that have this form. For any positive integer n, we get an eigenfunction and the corresponding eigenvalue. So this is our first important theorem of the section. And finally, I want to point out this other theorem, which I leave as an exercise for you. All right? Exercise. Prove this. The eigenvalue problem, same differential equation, but with different boundary conditions. Notice we're specifying that the derivatives are equal to 0, not that the function is equal to 0 there. We're not specifying the value of the function. We're just saying that the derivatives are equal to 0. It has the following eigenfunctions and eigenvalues. I listed the eigenvalue first, followed by the corresponding eigenfunction. It's got eigenvalues 0 with eigenfunction just constantly 1. And then we have the same eigenvalues that we had up here, one for each n, ranging from 1 to infinity, and the corresponding eigenfunctions using cosine this time instead of sine. Okay, so this is, I think, the core of what we needed to talk about for this section. And so that's it for this video. Eigenfunctions and eigenvalues for differential equations.